Okay, so hello everybody. So it's a pleasure to start now our fourth video conference organized today with the Nikon company. Nikon is one of the industrial partners of the GDR Imabio. So thanks a lot to organize this video conference with us. And Ignacio Isedin will moderate this session. So Ignacio is assistant professor to the ESPCI and is also member of the steering committee of the GDR Imabio. So Ignacio, if you can start.
Thanks, Virginie. And again, it's a pleasure to moderate this this seminar, which I'm very excited to listen to. So we're going to have two speakers today, as usual, someone from our Partners Club. In this case, it's going to be Sabrina Delattre, who is the European product manager of scanning confocal systems in Nikon Europe since the last 3.5 years, if I'm not mistaken. And well, Sabrina, I guess, is going to tell us about scanning confocal solutions in Nikon. And I just want to mention that she has a background mostly on neuroscience. She obtained a PhD in neuroscience in the University of Bonn under the direction of in the lab of Dietrich. And after the short presentation of Sabrina, we are going to welcome Giuseppe Vicidomini, who is going to tell us about how image scanning microscopy can be enhanced using a spat array detector. I will refresh very briefly the presentation of Giuseppe before he talks. I just want to mention now that he has a background actually at the beginning in computer science. He obtained his PhD in computer science in Genoa before moving to do a postdoc in the lab of Stefan Hell in Germany. And after coming back to Italy and spending some time as a postdoc again in the group of Diaspro, he is a PI and he has his independent research group at the Italian Institute of Technology since 2016. So without further ado, please, Sabrina Delattre, the floor is yours, and thanks again for accepting, both of you, helping us and organizing this seminar.
Well, thank you very much for the opportunity to be presenting you our latest add-on to our point scanner confocal, which is the Nikon Spatial Array Detector, the NSPAC. Before diving into the benefits of the NSPAC, I would like to briefly introduce you to the major improvements that the AX, our point scanner confocal, has underwent, which we believe has the most impact on a research study. First of all, we have the largest field of view on the market, which is 25mm diagonal. That is crucial with growing interest in spheroid and organoids, because it becomes more and more useful to use low magnification objective lenses, and increased field of view will always improve performance with such samples by maximizing the resolution and the speed. Laser scanning imaging can be challenging for specimen viability, as it applies laser focused illumination point by point onto the sample. Sorry. With the resonance scanner and its high speed, illumination time is reduced and thereby disturbance to the living sample. Reducing acquisition time also allows extremely fast acquisition speed up to 720 frames per second. And so fast dynamic events can be easily followed, as shown in here. Oh, by the way, do you see my, I guess you don't see my, my pointer. Now. So this here is a zebrafish blood flow, and you can see excellent image quality and resolution. And indeed, it's not working. And indeed, the AX can be coupled with scanning sizes up to 8K by 8K, and sampling beyond the optical diffraction limit is possible even at a low magnification objective lens. But the resolution of conventional microscope is limited by the diffraction limit of light, and the AX series remain a point scanner confocal with its inherent employment of a pinhole for better sectioning and rejection of out-of-focus light. To improve the lateral resolution, the pinhole needs to be closed to the minimum size, providing a diffraction-limited imaging system. There is a trade-off between the light collection efficiency and the resolution. So for dimly fluorescing samples, the pinhole can be open to a larger than 1 area unit, which then improve the contrast of the to the cost of the resolution. Similarly, the resolution can be improved by closing the pinhole, let's say to 0.2 area unit. So you will have an increase in resolution, but to the cost of a signal to noise. So with such a limitation, what can be done to overcome it? Well, Nikon has launched a new detector, the N-Spark for its nickname, that is based on image scanning microscopy principle that was developed at IIT, and that you will have way more information after my short presentation, thanks to Giuseppe Vicidomini. So the N-Spark consists of a 25 counting element to achieve a pinhole plane of 0.2 area unit. This detector array operates more like an extremely sensitive camera, where two-dimensional spatial information from each scanned pixel is collected by the detector. This 2D information is immediately used to obtain ultrafine structural information, which is lost in traditional detection. So a point scanning detector traditionally produces one intensity output. And so you can picture the detector, the PMT, as one big bucket. In contrast, the N-Spark, with its 25 output image, provide, so keep the spatial information at each pixel. And so the N-Spark has, as I mentioned, ISM principle, and it requires also a reassignment in order to have an improved resolution. So let me give you a little bit more explanation on how it works. This is going to be basic, and I'm sure Giuseppe will go in way more depth after my presentation. So the overall goal of reassignment is to send the signal from adjacent pixel back to the center. So if you look at the signal, the lateral PSF, at the edge of our 25 array detector, let's say here, we will have signal of 0.2 area unit, which is extremely dim. And also what you can see in the PSF is that it is deviated slightly from the center axis. If you move to the next pixel, which is closer to the on axis, you will have still a very dim signal because you are at 0.2 area unit, less dim than the previous one, and the deviation is of the PSF is a little bit closer to the center. On the center pixel, this is the best signal, still dark, of course, because it's a 0.2 area unit, but it is on center. This is equivalent to if someone would close the pinhole of a regular confocal microscope to a 0.2 area unit. The result when closing the pinhole would be high resolution, but to the trade-off of the brightness. Now, if we sum all of the pixel of our detector, so sum of all of the PSF, which is actually a confocal mode of our N-Spark, it is back to what we would have as a regular confocal of 1 area unit pinhole size. So the lateral PSF is actually the same resolution and brightness of what we have with conventional confocal microscope. Now, in order to have a resolution improvements while keeping the brightness, we are applying a pixel reassignment factor to pixels off-centered which is dependent on the pixel pitch onto the detector. So we can determine how far each pixel was off the center on axis. And this is, I hope you saw a little bit the animation here. So there is a vector shift. And by correcting this, we can replace the signal where it is belonging to. By doing so, we have therefore an improved lateral resolution and brightness. If you look at beads measurement, we can see this improvement in X and Y resolution. So on the side here, on the left side here, you have the AX GASP image acquisition, and on the right, the NSPAC. First, I want to point out to the very flat background with low count noise that we have with the NSPAC in comparison to the GASP PMT. So the SPPC is incredibly good for resolution because since noise is essential to signal-to-noise ratio, having a low noise with small standard deviation will make the NSPAC very sensitive and improved resolution. But measuring the full width half max of each of the beads in here in the field of view, you can see that we are very close to the actual size of the beads, which were 100 nanometer. This is hardware-based only, so one can think that with the convolution applied, we can have an extra boost in resolution. And having such an improvement in resolution brings more accuracy on studies like morphology or colocalization study. Here is an example of a rat hippocampal neurons. It's a courtesy of Christophe Leterrier, who provided us the sample. And it's a hippocampal neuron that was cultured for 16 days and labeled against MUNC13, which is a presynaptic marker, and a PSD 95, which is a postsynaptic marker. What you cannot see with the acquisition with a conventional confocal images is the localization between the pre and the post-synaptic marker. This is clearly visible with the NSPAC, what you can see in here, or here, for instance. We had also the chance to collaborate with Christophe Leterrier on another sample. So Christophe is the director of a Nikon Center of Excellence and expert in super resolution. And the question we wanted to assess was whether the NSPAC can resolve the actin rings seen with super resolution techniques. So indeed, one remarkable discovery of super resolution microscopy has been the periodic actin spectring scaffold along the axon with actin rings spaced every 190 nanometer by spectring tetramers. Here you can see a storm image that can clearly resolve this periodic pattern of actin spectrum. So naturally, we went to image with the NSPAC and acquired culture neurons stained against F-actin and beta-2 spectrin. And when we had a closer look into dendrite, we could actually resolve the periodic pattern of the actin rings, what you can see here. So the spacing between actin, the phalloid in here, imaging, and the beta-2 spectrin should be 119 nanometer. And so spectrin tetramers and actin rings are complementary. So the spacing between the two adjacent actin and actin and beta-2 spectrin should be half of 190 nanometer, which is 95 nanometer. And this is very close to what we achieve with the NSPAC. Another benefit of the NSPAC is that it can be paired to our gentle resonance scanner, which is ideal for live cell imaging. And since the morphology of mitochondria actively change over time, if the acquisition speed is slow, the image will be completely blurred, leading to a decrease in resolution. What we achieve here is a high resolution differentiation of the mitochondrial outer membrane, which is depicted in green, and the matrix, which is depicted in this pink color. What we observed here is the cristae structures within the matrix. And we could also see mitochondria fission through simultaneous observation of both the outer membrane and the matrix dynamics. So I think I managed to be almost on time. So what I would like you to have as a take-home message about the NSPAC is, first of all, that it's the first commercially available system that implements ISM technology. It has an improved resolution and signal-to-noise ratio. And what I haven't presented to you is that it's also possible to have improvement in depth. So it's basically ideal for morphology and colocalization studies. It can be paired with resonance scanner for gentle high-speed live cell imaging. Also, what I did not mention during the presentation is that there is no limitation in objective lens to be used. So it can use either low mag objective lens or high mag objective lenses. Of course, the resolution will not be similar to what I have been showing you this, but you will still have a gain in both signal to noise and resolution. And lastly, I haven't touched upon this, but it's very easy to use and it has an intuitive user interface. With this, I would like to thank you for your attention. And at the end of the session, I will be happy to answer any of the questions you might have. And for now, I'm going to stop sharing and leave the floor to Giuseppe.
Thanks a lot, Sabrina. Almost in time. As you said, yeah, let's keep the questions for after the talk of Giuseppe. Yes. And just want to mention something I forgot before for the public. As you know, the seminar is recorded. So if you don't want to be recorded and you want to ask a question, you can just write it in the chat, and I will ask for you. Otherwise, if you talk, if your camera is on, you will be recorded. Just be aware of that. Let's then move on to the seminar by Giuseppe Vicidomini. As I said before, he's gonna give us a bit more in-depth seminar about image scanning microscopy with SPAD array detector. So please, Giuseppe, the floor is yours. So whenever you want.
Okay, so thanks a lot. Thanks Ignacio, thanks Sandrine, thanks Virgin and Christophe and all the Imabio community to give me this opportunity to be here. Basically today, I want just to connect a little bit with the talk of that has been done before by Sabrine. And specifically what I want to do. So today I want to show you how a novel quantum technology and specifically a novel single photon detector array can somehow revolutionize and trigger what, to my opinion, can be the next generation of confocal microscopy. So yeah, let me start. I want to start with this slide that I don't think that I will shock you with this slide, in the sense that if I'm saying you, I think that you agree that if I tell you that the last 20 years, a little bit more maybe, of fluorescent optical microscopy has been dominated by the introduction of super resolution technique and their application to life science, you agree with me. So this is also depicted in this graph that simply show the number of papers dealing with super resolution microscopy published in the last 10, 20 years or a little bit more. So yeah, but if I show this slide, maybe you start to think a little bit more. So despite this domination of this super resolution technique, here I want to show the same graph that compare the publication that has been, I've taken a conventional database in which I simply add the keyword confocal instead of super resolution. And here you can clearly see that still confocal microscopy is dominating over super resolution microscopy. We have almost 3 times publication more. So yeah, super resolution microscopy is growing. It has an exponential growth, but still confocal microscopy is in our daily life when you are in a research lab, when you are in a life science lab. So the reason of this popularity, to my opinion, came to the fact that confocal laser scanning microscopy provide, first is a quantitative technique. So, and that's super important. So you want to have data. You don't want to have only pretty nice images. So, but anyway, offer you a unique combination of spatial temporal characteristics and give you access to many information of the sample. So, I mean, when you talk about confocal microscopy, I'm sure that you think about the opportunity to make three-dimensional images, so to navigate inside your sample, which can be thick, especially if you combine with two-photon excitation microscopy. What about temporal range? So, as has been shown already before, confocal microscopy is a pretty gentle technique. So you can make imaging of live samples, so specifically living cell. So what about temporal resolution? So it offers you a very decent temporal resolution. You can get frame of 100 up to 100 frames per second, especially when you combine with resonance scanner. And then you can get even more when you combine with other advanced techniques like fluorescence coloration spectroscopy. So pretty good temporal resolution as well. And information content, that's very, very important. So again, you don't want to get only simple nice image, but you want to get quantitative imaging. You don't want to understand the structure of your sample, but you want to understand the function of your sample. That's why one of the major strengths of confocal microscopy is that you combine with spectroscopy. And specifically, you can observe the spectrum of your dye and get more information, or you can measure the fluorescence lifetime of your dye. And at the end, I will show you that you can get even further information about your sample. So, and what about spatial resolution? So we start about super resolution. Anyway, confocal microscopies already provide you pretty good resolution. So it offers you subcellular spatial resolution. But that's enough? Not really. So otherwise we will not really, we are not here also talking about super resolution. So what I want to show you today is that image scanning microscopy, specifically the implementation based on our detector and the single photon detector array that I'm going to show later, can be really a sort of bridge that merge confocal microscopy with super resolution microscopy. But very important is a bridge that does not alter the performance of your confocal microscope. So you want to still have all the properties that I showed you before, adding super resolution. That's super important. You don't want to lose any aspect of your confocal microscope that is still one of the most used systems in your lab. So how image scanning microscopy can effectively achieve these results, I'm going to show you in a short. So, but before I need to explain you a little bit more about confocal microscopy and how, which is the limitation of this system in terms of super resolution. So it has been already mentioned before by Sabrine. So anyway, in a confocal laser microscope, what you do, you take a laser beam and use an objective lens to focus such a laser beam on your sample in order to generate a very tiny region to probe. So that typically is diffraction limited. So let's say it's in the order of 200 nanometers. The molecule, the fluorescent molecules that are in this region will emit light that are collected by the same objective lens. And then this light is projected into a photon sensor, typically a photomultiplier. So anyway, at the end of the story, we focus the light on a point and we register a single intensity value. So we measure the light that is coming from this region. Then, obviously, that's a laser scanning system. So to effectively build up an image, what we need to do is to scanning this laser beam across your sample and build up a bidimensional image of your sample. But what is important that you focus on a region and you collect a single intensity value to build up your images. So then this is a confocal microscope, or you can do much more. So a confocal microscope, you know the confocal microscope about the optical sectionability. And now you can get this optical sectionability. So, and why it is important? So first of all, because when you focus a light in a region, unfortunately, you don't focus in a planar region, so it's not only 200 nanometer in the lateral direction, but it's also pretty long along the axial direction. It's 600, let's say 3 times larger in the axial direction. So that means that you excite molecules that are also out of focus. So in some plane that are above and below of the plane that you are interested in. But likely, if you add a pinhole in the image plane of your microscope, so which is really a null, you can reject the light that is coming from the autofocus plane, as you can see here in this small graph, in which you can see that the light coming from in focus pass through the pinhole and reach your photomultiplier, while the light out of focus does not reach your photomultiplier because are blocked by the pinhole. So this graph show you what I explained you so far. So that's the diameter of the pinhole. If you close the pinhole, you can clearly see that you reduce basically the out of light up to 0. So you completely reject the autofocus light. So that's an example of a non-confocal image and the confocal images. As you can see, the image become much more crispy, much more detailed. You don't have this blur that deteriorate the quality of your image. So the pinhole, basically, you know the pinhole because the pinhole allow you to have optical sectioning and thereby having this three-dimensional capability. But something that maybe you are not aware is that the pinhole, in principle, can also provide you super resolution. So here is this graph show you that if I close the pinhole, I'm also able to reduce the size of the region from which I collect light. So the size of the probed region of my confocal microscope. So if I'm collecting basically the light from a smaller region and then scan this region, I can improve the resolution of my microscope. And specifically, I can improve the resolution by a factor of square of 2 in terms of full width maximum of my probed region. Or for people working in computer science like me, I mean, it's a question of information. And by closing the pinhole, in principle, you can doubling the frequency of your image. You can doubling the information transferred from your image. Exactly the same gain that you get with a structural illumination microscope. So if you reduce the pinhole, like in this case, as you can see here from this phantom example, you can improve the resolution. So you can get more detail about your image, as you can very clearly see here. You can distinguish more better this particle that you cannot distinguish when you have an open pinhole. So the question is now, okay, but confocal microscopy is a super resolution technique. So why people not using for that? The reason is practical. So because when you start to close the pinhole, unfortunately, you do not only reject out of focus light, but you also reject the light that is coming from the focal plane. So you close the pinhole, you shrink the probed region, but you completely cancel out the signal. So that's an hole. So light does not pass anymore through this hole. So here, for the very same example in which you you reduce the flux of photon coming from your sample, which is very typically in microscopy that your sample does not provide you enough signal. As you can see here, if I'm closing the pinhole, at one point I end up with noise, and noise is not information. So I don't improve effectively the resolution. So that means that when you sit in front of a conventional confocal microscope, in principle, you are sitting in front of a super resolution microscope, but in practice not, because you always have this trade-off between resolution and signal to noise ratio. So yeah, how it's possible to solve this problem? How it is possible to have a confocal microscope that is really a super resolution system? So that's exactly what people in the 80s start to think about. So in the funny things of image scanning microscopy, nevertheless, the name has been introduced later, is the fact that already in the 80s, two gentlemen, that was Professor Mario Bertera, Professor Colin Shepard, was already thinking to this problem, and they already came with a solution. So, and the solution is rather easy. They say, okay, why to use a single element detector? Why to use a photomultiplier in a confocal microscope and not using a pixelated detector, a camera, for example, and try to collect as much as possible information and then process this information to get out a super resolution images. So while the idea was in the 80s, unfortunately, I think that practically this idea could not be implemented because doesn't exist a camera that is so fast. So because you remember that you need to scan really fast your beam, and you would like to collect the data from each single probed region. So it took a little bit of time. I will skip all the history about image scanning microscopy because it was really clever people that tried to come out with some solution to take the idea of Colin and Bertera to implement a super resolution system. But I think that we have to wait up to a few years ago where we start to work on the idea of effectively introduce a detector that is perfect for image scanning microscopy. So basically a detector that is perfect to follow the scanning of the beam. So, and that's our detector that we introduced in 2019, that is a single photon detector and specifically a single photon Avro-dye array detector. So, but anyway, the idea is pretty old. So the fact that the idea is pretty old allows us to implement a detector that is matching with this idea, and very fast came out with an implementation, and nowadays also some commercial implementation are available. So, but let's give me a few details about this detector without too much into the digging of the electronic. But so as I told you, it's clear that the idea is there. And now I'll be going to tell you exactly how it works, the idea. but something is missing. So the detector is missing. So what we do, we knock to the door of Polytechnic of Milan, which are experts in spada array detector, and we designed the first detector specifically for laser scanning microscope. So yeah, what is this detector? This detector is very simple. It's a detector on only 5x5 element. So very small one, not a megapixel camera as the one of your mobile phone. But why we don't need a lot of pixels? Because how big is the probed region of your microscope? It's only 100 nanometer in size. It's a very tiny region. We don't need a very large camera. We need only 5x5 element. It's enough to sample properly this region and have a perfect image of this region. But since we have only 25 elements, we can transfer this data super fast. So basically, that's what we call is an asynchronous readout detector. Every time that a photon arrives in a single element of the detector, there is a digital signal that is fired to my data acquisition system. So there is no lag time. So there is no frame rate. So that's, in principle, is a camera without frame rate. That's the reason why you can combine with resonance scanning, that you can scan really very fast. Think that in a resonance scanner, you have a few nanosecond pixel dwell time. So a camera will never reach this speed. So now I have a camera that is really fast. So now let's go to the principle of image scanning microscopy. So as I told you, so the idea is to take this detector array that is super fast. You don't care too much about how much that you are scanning fast. And what you do, you remove the pinhole, you remove the photomultiplier, and you add in the image plane this detector array, this 5x5 detector array. So now I'm still scanning the system the very same way. Nothing changed in my microscope, only the detector changed. So, and now what I have, instead of having one single intensity value, I have a full image of my probed region, a small image of my probed region, but I have an image, a lot of information. So the idea of image scanning microscopy is to deal with this 4-dimensional data set, scanning coordinate, and then every scanning coordinate as a 2-dimensional image. So 4 different coordinates. So how I can deal with this 4-dimensional data set? Now I just make a small trick to show you this data set in a slightly different way. So what I can see is that try to think every element completely independent from the other one, which is true because that's a spada array. There is no frame rate. So every element is a completely different detector. So that is working in a completely parallel way. So if I think that every element of my detector is independent, I can think every element like to be a pinhole of my confocal microscope, because the size, the effective size of this detector is more or less 0.2 area unit, has been already described before. So it is 50 micrometer physical size, but then thanks to the microscope is reduced to few 100 nanometer in size, and specifically to 0.2 area unit. So every detector is able to generate an image, specifically a confocal image, because every element is acting as a pinhole. But all the detector itself is able to collect all the fluorescent light coming from the sample. It's not like before that I was throwing away light. Now I'm collecting all the light coming from my sample, and every element is producing me simultaneously a confocal images. So let's try to, now it's clear that we have these 25 images. What we can do, we would like to combine together to achieve super resolution, to get a single image with super resolution property. So, and to do that, we need to understand which kind of image we collected. And that's very simple, because in a confocal microscope, the point-point function is given simply by the product of your excitation multiplied for your detection point-point function. What does it mean this? That the excitation point-point function does not change at all, because this is still a laser scanning microscope. I do not make any change in the architecture of the microscope. What is changing is the detection point-point function, and each element has a slightly different detection point-point function. And in particular, which is the difference? It's very stupid. It's just simply a point-point function that is shifted, because my element is shifted. Every element is shifted with respect to the central element. So as you can see here, the point-point function of each element is this product. And this is the product of the blue line with the green line, that is the detection, and you end up with the orange line. You can assume that these are Gaussian functions. And you can see what happened is that I have different point-point functions that are simply shift each other. And this is what does it mean in terms of image, that the image is more or less the very same one for each element, but are shifted in space, one respect to each other. So that's the point-point function of my system. Every element of the 25 every element of the 5x5 matrix as a different point spread function. Here, the point spread function are represented. And again, in a bidimensional space, as you can see, they are really the same one, especially the one into the center, but they are simply shifted one respect to each other. Only the one in the periphery are slightly different, but more or less you can assume that all of them are Gaussian-like function and are shifted one respect to each other. So in the first approximation, the point spread function of each my scanned image, of each image associated to each element of the detector are identical, but just shifted. So if you think that this is the case, is that all the images are shifted, so what you can do to build up a single image is, so you can simply register these images and sum them up. And that's exactly the principle of pixel assignment. You take the 25 images, you shift it by a quantity that is called shift vector that can be easily obtained by making cross correlation, find the similarity between the 25 images, and then you sum them up. So at the end of the story, you have a square root of 2 enhancement in the full middle maximum of your point spread function, but you collect all the data. So you have super brightness effect. So you have you do not throw away photon, but at the same time you concentrate all these photon in a smaller region. So that's why you get super resolution. That's why you enhance the resolution of your microscope. So you are able to reduce the point spread function of your system without losing any photon. So collecting basically all the photon coming from your sample, or anyway, all the photon collected by your objective lenses. So I just add this slide to also give you the idea that you can treat in many different ways this data set. So pixel assignment is one approach. You can treat this data also in very stupid way, because what you can do is to sum up of all the images without any registration, and then you end up in a open pinhole confocal configuration. So very high signal to noise ratio because you collect all the data, but poor resolution because you don't squeeze the light. Or you can take the image from the central element, very stupid, because again, you have an enhancement resolution because it's a confocal microscope with a small pinhole, but you throw away all the light. So yeah, this is just to tell you that you have the data and then you can process the data as you like. The pixel assignment is just one approach. Here are a few results to explain you better. So in this example, that's the imaging of microtubulin, nothing so exotic. That's the image that I collect if I close the pinhole. So this is the intensity profile along this direction. Basically, it's only noise. If I close the pinhole, I reject all the light. If I open the pinhole, what happened? I increase the intensity, there is more light, more signal, but again, I don't have basic information, so I blurred my images. Now, but if I apply pixel assignment, as you can see here, the image becomes very crispy. The signal to noise ratio is excellent. As if you plot the intensity profile along this line, you are able, this red line, you are able to resolve these two tiny filaments that are in this region. So as a computer scientist, for me, pixel assignment was not enough. So we developed a series of algorithms, basically a series of multi-image deconvolution algorithm to further improve the image quality of the reconstruction. As you can see here, you further improve the contrast of your images and the signal to noise ratio. So again, you have information, now you need to merge this information. Pixel assignment is super nice because it's super fast. It can be implemented in a fraction of a second, but you can also use a more sophisticated algorithm to make it better, your reconstruction. So that's a very important slide. This slide, I want us to communicate the most important message. You get super resolution, but you do not destroy any function of your confocal microscope. That's a very versatile approach. You just need to change the detector, and then you don't have to change your sample preparation. You don't have to change nothing. So you sit in front of your confocal microscope, but you get super resolution data. So here is an example again of tubulin. That's another example which we was interested to study the chromatin organization. That's you can really appreciate how you can enhance the resolution in this imaging, which we was in a context of neuroscience. We was investigating this neuron spine. As you can see here, you can better resolve this neuron spine. Again, versatility is a key message. So that's a laser scanning microscope. Why not to use a two-photon excitation microscope, which is the method of choice when you want to go deeper? So that's an example of using the very same detector, the same microscope, but using a two-photon excitation source. As you can see here, especially if you compare the image scanning microscopy reconstruction with the non-scanned image that you typically get with a 2-photon excitation microscope, the enhancement in resolution is huge. And it's even higher than compared to the 1-photon excitation, because it's not a factor of 2 in terms of frequency, but it's almost a factor of 3. So you improve the signal to noise ratio, which maybe you are not interested, you are interested in super resolution. But if you improve the signal to noise ratio, it means that you can reduce the intensity of light that you project in your sample. And that means that you can acquire your sample longer. So that's a technique that is super useful in terms of long-term imaging. So if super resolution is your aim, that's great. But if long-term imaging and super resolution is your aim, again, that's the perfect technique to use. So I then want just to conclude with a few slides in which I give you a sort of perspective of the future. Again, that's a detector that opens so many perspectives, and I want just to give at least 2 examples. And one is still related to imaging. So as I told you before, when you close your pinhole of your microscope, what you do, you reduce also the autofocus light. So optical section is the fact that you reduce the autofocus light by closing the pinhole of your confocal microscope. Now I don't have any more pinhole. So what happened to my optical sectioning? In principle, I'm collecting autofocus light, and that's clear destroying my images. So when I'm dealing with fixed sample, that could be a problem. But I will not go into the detail, but what I want to tell you is that in your macro images, so again, you detect an image for each probed region. You do not only encode information about the lateral resolution, so the lateral distribution of fluorophore that you can use to improve the resolution, that you can use by pixel assignment, but you collect also information about the 3-dimensional distribution. So that's just to give you a flavor. That's an image collected from signal in focus. That's an image collected from signal out of focus. It's completely different. And now you get access to this information. So you can build up an algorithm that is able to discriminate from in-focus light and out-of-focus light. As you can see here, the enhancement in resolution is huge, not only because I apply pixel assignment and I'm able to basically achieve this double in terms of this double resolution, but also because I reject out-of-focus light. So this light is only out-of-focus light, and it's obviously that I'm not able to reject, then my image will be not really very detailed one. So with this system, I'm not only able to improve the lateral resolution, but I'm also able to improve the optical section, and thereby getting also enhancement in the axial resolution. Last but not least, I did not mention so far, I just tell you that this is a single photon detector, but that's also a timing detector. So for each photon that arrives to your single element detector, I can register the so-called photon arrival time with a precision of 100 picosecond. And 100 picosecond is a precision that gives you access to the photophysics of your molecule. So what does it mean? Is that I can combine that I have, if I'm able to record the position of this photon, so to get these micro images, but I'm also able to record the photon arrival time. I don't have only an enhancement in resolution, like I show you so far, but what I can do, I can combine also with fluorescent lifetime. So the very same data set can be used to build up a super resolution images, but can be used also to build up a super resolution fluorescent lifetime images. And fluorescent lifetime image is so important when you want to combine structural illumination with structural imaging with functional imaging, because thanks to fluorescent lifetime, you are able to, for example, to understand the nano environment of your molecule of interest. You can understand, for example, which pH is the molecule, which is the oxygen or ion concentration of the molecule. And even more important, is the molecule interacting with some other partner, is doing something, which is the function of this molecule. So these are a few examples that we are running into our lab. For example, we are using fluorescent lifetime image scanning microscopy, and specifically fluorescent lifetime, to understand where a channel, an ion channel is open, because fluorescent and also GFP is the lifetime of GFP, and in general fluorescent is sensitive to the ion concentration. That's another example in which we are interested to understand the order of the lipid in the membrane, and lifetime is able to tell me, okay, the lipids are in an order phase, the lipids are in a disorder phase. For example, in the plasma membrane, you see a longer lifetime, yellow more or less, that tell you that the lipids are in an order phase. While in the inner vesicle, the lifetime is shorter because they are in a disorder phase. So structural imaging combined with functional imaging. And everything is in live. That's super important. That's a system that improves your light cell imaging because you can reduce the light that you need to project in your sample. Very last slide. Yeah, that's really the tip of the iceberg. So I just give you a little bit, I hope that I was able to introduce you the idea of this detector that is able to sampling photon in space and time. But I just show you the tip of the iceberg because I just show you how you can combine this detector to achieve super resolution by image scanning microscopy and combine with forest lifetime imaging. But there is much more because you can combine with forest coloration spectroscopy to investigate the dynamic of your molecule. You can combine with STED to further improve the resolution of STED microscopy. You can combine with adaptive optics when you are interested to go deeper, and you can combine with single molecule imaging and tracking. So really, that's a detector that can really open so many perspectives in laser scanning microscopy, not only in confocal laser scanning microscopy. With this, I want just to end my talk, and thanks all the people involved in this project, specifically my group. All what I'm doing is thanks to them. Without them, I would be not here. I want to thank Nikon to support my research, Polytechnic of Milan for the development of the detector, the group of Professor Diaspro for the support, and the funding agency, and not least also Genoa Instrument, that is a startup that is developing this detector right now, that is commercialized this detector right now. So thanks a lot for your attention. Okay.
Well, thanks a lot for this very interesting and clear seminar. Let me check if there are questions in the chat. I don't see. I have a couple of questions. In the meantime, if someone has a question, you can just type it in the chat if you want me to read it, or simply raise your hand and we'll give you. I see Virginie who is raising her hand, so so please go on.
Yeah, I have just a short question about the film part. I presume that you need to have a pulse laser source in this case, or I'm wrong?
No, it's true. So what we do, we implemented conventional time correlated single photon counting measurement. I may say conventional, not really, because people when think to time correlated single photon counting, always think about I'm losing photon. That's not really true. So, but anyway, you need a pulse laser. So you need to synchronize your excitation with your detection. And this is typically done with a pulse laser. Yeah.
Okay, thank you.
I have another question. It's a bit interested question, and I see that you have a paper and a preprint. So my question is, how does it compare localizing single molecules respect to a camera base?
Okay, so this detector array, this specific detector array, this specific SPAD array detector has been designed to have this asynchronous readout. So every photon is transferred to the data acquisition. So that means that to keep this function, we need to have only a few elements. So that means that it's a detector that can be combined with single molecule imaging or with this class of technique that nowadays are called sequential structural illumination single molecule microscopy. One of the most famous one is mean flux. So, and if you think mean flux, it's a laser scanning microscope. So it's a laser scanning microscope that is scanning in a very smart way around the molecule. And then you collect the data with a single element detector. But think about if you have an image of each scanning position. So for sure, this information can be used. And by free, we can doubling also in this case the resolution. We have the square root of 2 enhancement also in single molecule.
Okay, but MinFlux is following the particle, while your approach would be to create an image and detect the particle on the image, right?
The other beauty is that one of the is not a limitation. I mean, I'm not saying something about MinFlux, bad about MinFlux, is that you need to know that the molecule is into the center of your scanning. Basically, because you don't have an image of your molecule, but now we have an image, so that's anymore a constraint. So basically, we have a larger field of view compared to MinFlux. Then obviously you can scan across all your sample to build up a large image and increase the field of view. But what I want to say, you also in these cases, you introduce an element that provides you more information, and by elaborating this information, you can gain in localization precision, for example, in MinFlux.
Okay. There are a couple of questions in the chat. There is Huyen Shu who is asking, does the array detector change axial resolution? And I have somewhat related question from Aurélien Barbotan, who is asking about the penetration depth. How well does imaging scanning microscopy handle aberrations and light scattering as compared to confocal?
Wow, a lot of questions, a lot of really interesting questions. And we deserve a longer.
So the first one was about the axial resolution.
No, yeah. Anyway, so I just give you a sort of introduction of a project that we are working on to use this detector array to improve also the axial resolution. And yeah, so these are a little bit more complex algorithms. It's not a pixel assignment, it's a maximum likelihood algorithm. So, but yeah, we can improve the axial resolution because, as I told you, the detector, having an image of each probed region encode also information about the axial position of the structure. So we can decode this information to improve the optical section. And that's one issue. Then another issue is about the deep. Okay, clearly, if you want to go deeper, if you open the pinhole, so we are working typically with a detector that has 1.4 error unit. So you start to collect autofocus light, and thereby you need to process this data. So it's become fundamental to dealing the data in a slightly different way. Then another cool aspect is that these micro images, it's easy to demonstrate that they encode information about the point-point function of the system. Since they encode information about the point-point function of the system, they encode information about the aberration of your system. So we have a project in which we use this detector as a wavefront sensor to recover the aberration of the system and then to compensate with some digital mirror device or some adaptive optics element. Last but not least, that can be combined with two-photon excitation. So if you ask me number, how deep I can go, I think that's just a question of sample. But I have a lot of different strategy to make this system suitable for deep imaging. Two-photon, adaptive optics, optical section enhancement. So, and this everything can be, I'm sure that it will be implemented also by Spark and so on. So this detector opens so many perspectives, give you access to many information that you can process to match at the best imaging for your sample.
Thanks a lot for the answers. There is another question for Sabrina, and I also have a quick question for Sabrina. So Huyen Shu is asking in the chat, what does AX mean?
There is, well, no real meaning for AX, but actually the A was for our series of confocal. One was the first confocal, well, actually not exactly the first one, but the X is for the 10th generation, basically. So this is it. And I just wanted to add something on the penetration depth. So with the NSPARC, we actually can see really an improvement in signal to noise up to 200 micron or so. So this is very impressive. And also what I wanted to add is that we have an MP NSPARC that can be coupled with our MP version of the AX. So we have also the possibility to have a gain in resolution and signal to noise also with the MP.
Okay, and I just have a technical question also for Sabrina, and after that, if there are no more questions in the chat, I will give the word to Virginie to close the session. So I just wanted to know, it's an asynchronous scanning, so what is the frequency of scan, if you have that in mind? And if I understand correctly, there is no synchronization to be performed, right? So the mirror is scanning freely, and there is no synchronization with any other element of the system? Or am I seeing that wrongly?
No, well, so actually our NSPARC is directly coupled to our scan head. So we can directly use the galvano mirrors or the resonant mirrors. And so then there is basically we are, so I guess you wanted to ask, well, correct me if I'm wrong, but I guess you wanted to ask about the pixel.
The scanning frequency.
Yeah, the pixel dwell time or the scanning size, right?
Yeah, what is the pixel dwell time? The time to go
This
from
will be, yeah, this will be exactly the same as what we have for our AX. Our confocal microscope is really an add-on of the confocal microscope. So you can have from 0.2 to 0.2 microsecond to 2 millisecond with our Galvo scanner. And yeah, the pixel dwell of the resonance scanner is very fast. So we are lower than 0.2 microsecond for sure.
Okay, so if there are no more questions, let me check. There is no raised hands, no questions in the chat. So thanks again to both of you, Sabrina, Giuseppe. You can clap with emojis in Zoom. And well, I think Virginie is going to close this session. Thanks again, and I find it very interesting. You'll have both an email from me tomorrow.
Thanks.
Thanks a lot to Sabrina and Giuseppe for this nice session. Thanks also Ignacio to the moderation of this session. And so the next meeting will be with Abelite, and it will be on Tuesday, 6th of February, because the first Tuesday of the year will be very early. So so it's why it will be the 6th of February. So thanks a lot to everyone, and see you soon.
Thanks.
Thank you very much.
Thanks a lot.
Bye-bye.
Bye, Ignacio. Bye, Sandrine.
Bye. Thanks.
Bye.